Hi guys, so in this video, recall we've been able to handle decoders, handles 2-line to 3-line, 3-line to 8-line. Now we're going to look at one of the most familiar examples and applications of decoding circuits, which is the 7-segment display decoder. All right, you've definitely, most likely, if you've handled a digital watch, most digital timers, numbering systems use 7-segment display decoders. So we're going to be able to see how to design one ourselves, design the decoder for it, and see what we can do to get even the function table for such a decoder. All right, so the first thing we're going to cover is binary coded decimal. Okay, BCD stands for binary coded decimal. What does it mean? It is plain simply the same as binary. All right, but it's binary is a binary numbering system where I'm using a binary sequence to indicate a number in decimal. All right, so 000 0 would be 0. So if this is binary and this is decimal, okay, base 10, base 2. 0001 would be 1. 0002 would be pardon me, okay. 0010 would be 2 in binary. 0011 would be 3. 0100 would be 4, and so on and so forth. Okay, so that's the objective of a binary coded decimal. I need to be able to use a binary sequence. All right, so if I have an output and I say, okay, low, high, low, high, right? So this would be 0, 1, 0, 1, and that's to be 5 in decimal. Okay, so this is pretty simple. That's what happens when we deal with binary coded decimals. All right, so now we're going to look at the 7 segments display. So it's drawing it looks something like this. Okay, it's made up of 7 segments, and you can really use it to represent any number from 0 to 9, as well as there's a way you can use it to represent letters as well. So each of these segments is numbered clockwise this way. So A, B, C, D, E, F, and the middle one is a G. All right, so now it's going to look much more familiar. So the idea is that if I want to represent any number from 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So let's say we want to represent 3. You can now figure out that, all right, if I shade A, shade G, shade B, shade C, and shade D, then I'm going to have something that really looks like a 3. If you can squint your eyes and imagine it done correctly, right? So if we were to represent this, we can say 3 is going to be A, B, C, D, G. Okay, A, B, C, D, G. So that's the entire logic so A, B, C, D, G. Okay, so let's say A, B, C, D, G. We can do the same thing for any other number. Let's say 1 that represents 7, right? So shade A, shade B, shade C. So that's going to be ABC is going to represent 7. So that's the logic when dealing with 7-segment displays. You have numbers from 0 to 9, and you want to be able to show which sequence of segments do I activate to make such a number come alive. All right. So now we're going to look at drawing the truth table for it. So let's draw one this way. So we have one for reference. Okay. So we have a 7-segment display for reference. 1, 2, like so, and like so. All right. So how this is going to work is that we're going to have 4 inputs. Okay, D, C, B, and A. The reason for 4 inputs is that we're dealing with numbers from 0 to 9. And recall the decoder is able to take n inputs and transform it to at least 2 raised power n outputs. So 0 to 9 is 10 digits. Okay, so we need a number of inputs that are going to give us an output line greater than 10. So 2 raised power 4 is 16. 2 raised power 3 is 8. 8 is not going to be sufficient for us. So that's why we use 4 inputs when dealing with a sequence. All right. So we label this A, B, C, D, E, F, G. So we can do the same thing here. A, B, C, D, E, F. The final one is going to be G. And our decimal number. Okay. So we can call this number. Remember, we'll do with this as we normally fill 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, go 1, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Remember, we've not exhausted all the possible combinations for 4 inputs in binary, right? So if we were to go and then do 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. These will be what we call don't care, okay? So don't care are binary situations where it's out of the domain of what is specified. This means that we're going to write 10, and you cannot write 10 in decimal with only 1 digit, okay? So that's the reason we make the rest of these don't care. So we're going to see if we can go ahead and get the configurations for a number of outputs. So if we were to make a 0, okay, we know that that's going to be A, B, C, D, E, and F. Okay, highlighting everything around is going to give us a 0. All right, so A, B, C, D, E, and F. So that's going to be 1, 1, 1, 1, 1, 1, 0. So that's how we go on in handling. Okay, so let's work backwards this way. Okay, so that's how we go backwards in handling logic 1, 1, 1, 1, 1, 0. All right. If we're to do the number 1, because all we have to do is just the leftmost 2 bits. So that's B and C. So B and C will be high, and everything else is going to be low. If we're to do 2, it's going to look something like that. Okay, so it's pretty fun. So that's A. Okay, let's make it bigger. So that's A, B, C is going to be ignored, D, E, and G. So we're going to make A high, B high, skip over to make D high, E high, and make G high. Fill the rest as 0. For it to do 3. Okay, so that's everything except F and E. So E and F are going to be 0. I'm going to fill everything else as a 1. If we were to do, let's say we wanted to do 6, for instance. Okay, 66 is going to be 1, 2, 3, 4. So B is going to be ignored. So B is going to be 0. So we're 6. I'm going to fill the rest of this as high. If we were to make 6. Okay. So I'm just going to go ahead and fill the rest of these so that we can get an idea of what's. Okay, you know what? Let's just go ahead. So for 4. Is that how to write 4? Okay, yeah, it's this way. So that's going to be B, C, F, G. So that's B, C, F, and G. Okay, so you can see the process we're going through. If I wanted to make it 5, okay, so that's A, C, D, F, G. So A, C, D, F, G. Fill the rest as 0. And if we were to fill 7, it's going to be 1, 1, 3 1s, the rest is 0s. 8, everything is going to be asserted. And for 9, only E is going to be off. Okay, so you can really play around with it and see how we really come around doing this from physically determining which of the segments should be activated. So this is the function table for the 7-segment display and is a very important application of a decoder. So sometimes if you're able to sit down and think, All right. Can I make a kernel map expression for the segment D? Then you'll be able to do that. All right. Map everything you have here to the kernel map, and then fill the rest as don't cares, and then try and make the simplified expression. So if at the end of the day you have simplified expressions for A, B, C, all the way to G, then you'll be able to perhaps create your own number generator. So you can see how really interesting this is, right? If we were to usually do this without decoders, then if I wanted to write number, let's say number 3, for instance, I'll have to send a binary signal of 11110001. But because I'm using decoders, I can simply just send that DCBA is just going to be 0, 0, 1, and 1. And I'm going to perform the 4 to 10, because it could be 4 to 16, right? But I'm using only 10 outputs, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to perform the 4 to 10 decoder and end up with my outputs. So we can see the really advantage we have when using decoders. All right. So thanks for watching. If you do have any questions, anything you pointed out, whatever you think is wrong with the video, and a better explanation to a question, or just something you think is odd about the way we use binary coded decimals, please feel free to leave a post in the community or highlight us on the comments. So thanks for watching. I'll see you in the next video.